Okay, so in this video, we will solve problem 4b of problem sheet number 8, and we will provide an elementary proof. We are only going to use a Venn diagram and the very definition of conditional probabilities. So if you recall here, there were two key events, the event that twin A succeeds and twin B succeeds. I will abuse notation a little bit here and define event A as the event that twin A succeeds. And similarly, the event B as twin B succeeds. So these two are the fundamental events, and we're given 3 bits of information. The probability that A succeeds is 0.5. The probability that twin B succeeds is 0.7. And the probability that both twin A and twin B succeed is 0.4. And given this information, the question is B is asking for the probability. I'll write it here. No, I'll put my Venn diagram here. I'll write the probability here that we want. We want the probability that twin A fails. Well, a failure for twin A is the complement of event A. So if event A is twin A succeeds, the complement of A is twin A does not succeed, therefore fails. Given that twin B has also failed, so again B is the event for twin B succeeding, B complement is the event twin B failing. This is the probability that we want to find given these 3 bits of information. This may seem complicated, and what we're going to show is that it actually is absolutely elementary if we just visualize the problem, again using a Venn diagram and going back to the very definition of conditional probabilities. So let's produce a Venn diagram. It will be fairly simple as there are only 2 events, events A and B. We'll label S the sample space. So event A, event B. Now you have to be careful here. You can't enter 0.5 here because that's the probability of A. The entire region occupied by A has a total probability of 0.5. So it's not true that the probability of this region is 0.5, right? The total of A is 0.5. The same goes for the 0.7 for B, but we have the intersection. This region is not divided up into multiple subregions, and so the probability of A intersect B, what's common to A and B, is 0.4. So we know this. And from this point we can complete the Venn diagram. If the total probability for A is 0.5, well, if we have 0.4 here, we're missing 0.1 here. And the same goes for B. Total probability for B is 0.7. We already have 0.4 here, so we're missing 0.3 here. And finally, for the complement of both, the probability of the sample space is always 1, as the sample space contains all possible outcomes. So the total must be 1. Well, how much do we have in here? 0.5 plus 0.3, 0.8. That leaves us with 0.2 for the remaining region. Now we have a complete Venn diagram. Let's see how we can now easily find this probability from the very definition of a conditional probability. So if you remember, when you're given P of an event given some other event, what this means is that since we know this has occurred, this is now our new sample space, right? The sample space contains all possibilities. So initially, we have to look at the whole sample space of probability 1. But now we're given that the complement of B has occurred. So we know for a fact that this event has occurred. This is now our new smaller sample space. Well, what is it? This is the complement of B, so everything outside of B is now the new sample space. So this is B. B complement is everything outside of B. So let's cross off B. This is saying not B. Everything except for B. So let's cross off B. This is no longer part of our sample space. So the sample space now is a whole lot smaller. What remains is B complement. And again, a probability is nothing more than a proportion. So out of the total probability area of the new smaller sample space, which is 0.2 plus 0.1, so out of a total probability for the new sample space of 0.3, we are asking for the probability of the event A complement, which means not A, everything except for A. So if you remove A, what are you left with? A total of 0.2. And so, if you think of multiplying by 10 to cancel the decimals, what you have is simply 2 out of 3. If you want to go back to decimals, this is about 0.67. And that's it. So the lesson here is, if you're not sure how to approach solving a particular problem, always try the simplest approach, which is going back to the very definition. If you can visualize the information given in a sample space, that's always a good approach. And if you attempt to calculate a conditional probability, try to do it from the very definition, simply by shrinking down to the new smaller sample space. Here it was B complement, so everything outside of B was now the new sample space, and out of this total of 0.3, how much is occupied by the event of interest? Here this was A complement, everything outside of A, 0.2. If this approach works, fantastic. If it doesn't, then start thinking of using more advanced techniques, more advanced results, properties of probabilities and conditional probabilities. But if you're not sure how to approach a problem, the first thing you should always try is do it from square one, the very definition of conditional probability, being just a probability as the ratio of two quantities, the thing you want over all possibilities given the new smaller sample space.